Hey, welcome back. In this video, we're going to discuss pursuit-evasion games on graphs. We're going to focus on one game in particular, which is probably the most famous pursuit-evasion game that's played on graphs. And this game is called the cop versus robber game. There are other pursuit-evasion games that are not played on graphs. One that's played in the plane, for example, is called Man vs. Lion. There's many research papers on that. A lot of them are earlier than most of the research papers on cop versus robber. But we're going to focus on cop versus robber because this one's played on graphs and this course is about graphs. So with cop versus robber, we start with some graph G. So I'm going to draw a graph. Here's just some graph. And we're given that graph. That'll be G. And at the beginning of the game, the team of cops choose their starting vertices. So when we're playing cop versus robber, we might have only one cop on our team. We might have any number of cops. So we could have 10 cops. We could have 2 cops. Let's say in this case, we have 2 cops. And we'll put one of them right here and one of them right here. So those will be the starting positions for the 2 cops. Once the 2 cops place themselves, or however many cops there are on the team of cops, then the robber chooses their starting vertex. So in the cop versus robber game, the cops always choose their initial positions first, and all the cops choose their initial positions, and then after that, the robber chooses their initial position. So let's say the robber goes here. Now, each turn of the game, the 2 players will alternate. And just as the cops placed initially and then the robber placed themselves second, with the turns, the team of cops goes first and then the robber goes. So on cop turns, any of the cops on the team can move to some adjacent vertex or stay at the vertex where they're currently at. So for example, the first turn of the game, this cop can go right here on the first turn. And this cop can go right here, also still on the first turn. And on that first turn, the second part of the first turn, the robber goes. So the robber always goes after the cops each turn. And on the robber part of the turn, the robber is allowed the same options as the cop. The robber can either move to an adjacent vertex or stay at their current vertex. In this case, with the graph I drew, the robber would have no advantage to move to an adjacent vertex because moving to an adjacent vertex would put them right on top of a cop. And they don't want to do that in this game. The robber wants to stay away from the cops. So the robber would just stay at their current vertex in this situation. And the rules for winning and losing, we say that the cops win if some cop eventually is at the same vertex as the robber. And the robber wins if they are able to evade capture forever. And we assume with this game that both the cops and the robber play optimally. So both the team of cops and the robber play to win. And I'll mention for that graph at the top, so we talked about what happened on the first turn. The first turn, each of the cops moves a step closer to the robber, and then the robber didn't move because if they moved at all, they would end up at the same vertex as one of the cops. On the second turn, only one of these cops has to move, so this one can move, and they end up at the same vertex as the robber. This cop could also move if they wanted to. It doesn't hurt anything. So we get double cops there if we wanted to. And it only takes one, but having at least one of the cops on that same vertex as the robber means that those two cops win that graph. So the cops win on that graph if we use two cops. And we can see that regardless of how the robber plays on that graph, if we do have at least two cops, the cops will win on that graph. There are a number of applications of this game. So besides the obvious intuitive application of a team of cops actually chasing a robber through some network, like a network of roads or a network of hallways and stairways in a building, there's more realistic applications. So there's been multiple research papers where they apply strategies in this game to coordinate mobile autonomous agents. It's also been used for routing reconfiguration and graph decompositions. So I want to discuss a few terms and look at some examples of graphs just to illustrate what these terms mean. One of the most basic terms about the cop versus robber game is this term cop win. And we say that a graph G is cop win if a single cop can always catch the robber in G, regardless of how the robber plays. A single cop playing optimally can always catch the robber in G. That's what it means for G to be cop win. So here's an example of a cop win graph. If we take the path P sub n for any n at least 2, this is cop win. And here's one way to see it. And the strategy I'm going to use here, this is not an optimal strategy in terms of the amount of time it takes the cop to capture the robber, but this strategy does show that the graph is cop win. So let's say we just place the cop right here on the first turn. And I shouldn't say first turn, I should say we place them there on their initial position. The first turn is when the cop actually moves from their initial position. And if the cop is placed there, then the robber for their initial position is probably going to place over here as far away from possible as possible from the cop. So on the first turn of the game, the cop always goes first. And so they will move towards the robber. That's turn 1. They end up here. Turn 1, the robber would be smart just to stay where they are. And then on turn 2, the cop will move a step closer. Robber still stays in place. And cop continues to move closer, and robber continues to just stay where they are. And finally, the cop takes one more step. So the 5th move of the game, the 5th turn, the cop ends up on the same vertex as the robber. And that's assuming that the robber plays optimally and does not move towards the cop. And we can see that if the robber did move at all towards the cop would only capture the robber sooner. So the amount of space that the robber has where they are safe decreases by 1 each turn, regardless of how the robber moves. So on the path P sub n, the cop is guaranteed to capture the robber in at most n-1 turns with how we've drawn it here. So placing the cop on this left endpoint, we can see that the cop can capture the robber in at most n-1 turns because they took n-1 steps here. In this case, we had a P6 and they took 5 steps. With a Pn, it would be n-1. And it's only n-1 if the robber plays optimally for that cop position. If the robber steps closer to the cop, then the cop could possibly capture them earlier. But the cop is guaranteed to capture them within n-1 turns. So we can see easily the path Pn is cop win. And the number of turns that the cop took to capture the robber n-1, we'll see that we can do a lot better than this. And you can think about what cop position would give us a better capture time. But we'll talk about that a few slides later. So we had a cop win graph there. Let's look at a graph that's not cop win. So the cycle of order at least 4. Let's see why this is not cop win. So let's suppose the cop places somewhere on the cycle for their initial position. By symmetry, any initial position is the same. So we'll just place the cop right here. Now the robber, wherever the cop places, since the cycle has order at least 4, the robber can place 2 away from the cop. Exactly 2 away. So if the order is exactly 4, then the robber will be distance 2 this way and distance 2 the other way. If the order is more than 4, then the robber has distance 2 only this way. Now, wherever the cop moves for each turn of the game, the robber, right after the cop makes their turn, can move at least distance 2 away from the cop. So if the cop moves any closer to the robber, so on the first turn, let's say the cop goes here, then the robber on the first turn just goes here. And then the cop might go here, but then the robber on the second turn will go here. And it will just continue like this, where the distance between the cop and the robber stays exactly 2 at the end of each turn. So when we have a cycle of order at least 4, then it's not going to be cop win. If we have a smaller cycle than that, though, then it is cop win. So we can look at this cycle of order 3, and we can place the cop right here. And we can see that wherever you place the robber, place it here, or you can place it here. Either of those places, placing it at either of them is equivalent. The cop on the first turn of the game just gets the robber. And we will always have the graph be cop win if there is a special kind of vertex called a universal vertex. So universal vertex, it is adjacent to all the other vertices. So in this cycle of order 3, another name for the cycle of order 3 is the complete graph of order 3. And so in the cycle of order 3, any of the vertices are universal vertices. All of them are adjacent to all the other vertices. And this is true in general for complete graphs. Complete graphs, all of the vertices are adjacent to all the other vertices. And any graph with a universal vertex, it's going to be cop win. And why does that make sense? Well, you can just place the cop on the universal vertex like we did right here. So the cop's initial position is right on that universal vertex. And that means that no matter where the robber places, on the first turn of the game, the cop can just go right to the robber's vertex, and then the game's over. So with a universal vertex, the game is very simple. The cop is guaranteed to win. So we had this term cop win. We saw some examples of graphs that are cop win or not cop win. Here's another term, C of G. it's a function. It's a function that takes an input, which is a graph, and it outputs a positive integer. And that positive integer, C of g, is the smallest number of cops required to catch the robber in G. So in other words, the smallest number of cops required to guarantee victory in G. So let's look at a few examples of graphs and the C of G function for those graphs. And this C of G, it has a name in words. It's called the cop number. So the cop number of G. And that is denoted as C of G. So for example, if we look at the cycle of order n, for any n at least 4, the cop number of this is going to be 2. We saw that the cop number is not 1 because C of n is not cop win. So that implies that the cop number of Cn is strictly greater than 1. So the cop number can only be 1 when the graph is cop win. So we know cop number of Cn is greater than 1. And we can prove that it equals 2 by seeing that it's less than or equal to 2. And to see that it's less than or equal to 2, all we have to do is provide some strategy that 2 cops can use on Cn that can guarantee that the robber will be captured. So here is one possible strategy. We take the Cn and we place the cops at any 2 vertices of the Cn. So for example, we could place them close to each other, like here. This would be fine. This will not be optimal, but it will guarantee victory. And let's say the robber places anywhere in Cn. If the robber is smart, they're going to be as far away from the cops as possible. So put them over here. And the strategy that the cops are going to use to capture the robber is they're just going to close in on the robber from both sides. So what does that mean? Well, this cop is going to go around this side, and this cop's going to go around this side. The robber is just going to stay in place. And we can see that on the 4th turn, regardless of what the robber does, by the 4th turn, the robber is guaranteed to get captured by these 2 cops. So it's possible to get captured even earlier than that. But if the robber plays optimally for that initial position of the 2 cops, then on the 4th turn is when the robber will be captured. And we can actually do better than that. So instead of placing the 2 cops next to each other, we can place them in a different way. And we'll see that in a few slides. So if we generalize this strategy that we just used to any n, then we would see that the amount of time that it took these cops to capture the robber was approximately n over 2. And we can actually do a lot better than n over 2 for the cycle. But again, we'll see that in a few slides. So we saw that this strategy guarantees that the robber will be captured. So this is why we have this upper bound right here. And together, the lower bound and the upper bound imply that the cop number is exactly 2 for cycles of order at least 4. So here is another example So we talked about universal vertices. So let's look right here. We have a star. So it's K1n for some n. And stars are another graph that have universal vertices. Stars have a single universal vertex, the vertex in the center. And any graph with universal vertex is going to be Copwin. So this is why we can say that stars have Cop number 1, since they're Copwin. And the complete graphs, as we discussed earlier, they also have universal vertices. So all the vertices in the complete graph are universal. And we saw that complete graphs were Copwin. And by definition, if a graph is Copwin, it has Cop number 1. So this is why we can say that complete graphs have Cop number 1. So here is a problem for you to think about. Can you find the Cop number of the complete bipartite graph with parts of order m and n? And this is for any m and n that are at least 1. So let's look at another term, and it's related to something that we were talking about on some of the last few slides when we were looking at the path and the cycle. So we were considering how long it takes to capture the robber. And we define another function for this. So we had the Cop number right here. That's the Cop number of G. And this function at the bottom is called the capture time of G. Capture time of G denoted capt of G. And this is the smallest number of turns sufficient for the Cop number of G cops to catch the robber. So I want to note something very important about the definition of capt G here. When we calculate capt G, the number of cops that we have to use, the number of cops we use is equal to the Cop number of the graph G that we're considering. And different graphs have different Cop numbers. So when we talk about the capture time of one graph compared to the capture time of another, we might be using completely different numbers of cops on each of those graphs. And we're going to see some examples of this on the next few slides. One other thing I'll mention here is for capt G, we assume that both the cops and the robber position themselves and play optimally. So the smallest number of turns sufficient for the Cop number of cops to catch the robber. In order to make that number of turns as small as possible, the cops are going to position themselves to minimize that number of turns. And we'll see this on some simple graphs. So for example, if we consider the path of order n, and when we want to calculate capt of Pn, the capture time of Pn, we want to find the smallest number of turns sufficient for the Cop number of Pn cops, so C of Pn cops, to catch the robber on Pn. And remember that C of Pn, we proved on an earlier slide that this equals 1. So for capt of Pn, we're trying to find the smallest number of turns sufficient for just a single cop to catch the robber. And that's regardless of how the robber plays. So we're assuming that both the cop and the robber use best possible play. So the cop has to guarantee that regardless of how the robber plays, they can capture the robber in at most capped of PN turns. So where should the cop position themselves? The best place to position themselves is as close to the center of the path as possible. So if the path has odd order, then there's a single center. And if the path has even order, then there will be two centers. So the cop will have two choices of where to position themselves when the path has even order. And we can see that if the cop does position themselves close to the center of the path, the capture time is approximately n/2. Regardless of where the robber goes, the robber can go over here or they can go over here. And the cop will just step towards the robber each turn of the game. And since the cop is in the center and the total length is n, in order for the cop to capture the robber, the cop has to take at most n/2 steps, approximately. And so that's why the capture time is approximately n/2. Although we only explained really why the capture time is less than n/2. And the reason why we can see that it's also greater than n/2 approximately is because wherever the cop does place himself, so we have some path here, the cop places himself somewhere on the path. If they place himself closer to the left side, then the robber will go to the right side. And the cop places himself closer to the right side, then the robber will go all the way to the left. And we can see that the cop will take at least n/2 turns to reach the robber if the robber just stays put at wherever they started. So that's why the capture time is approximately n/2 for the path. And the reason for this is really because the cop number of the path is 1. We only have one cop to use on this path, so it can only really split the path in half. Let's look at another graph that we saw earlier, the cycle. So with the cycle, initially when we were proving that the cycle had cop number 2, we used a strategy where the cops were next to each other. But a smarter strategy, if we want to minimize the capture time, is to have the cops start approximately diametrically opposite. So one of the cops starts here, one of the cops starts here. Then the robber positions himself anywhere in the graph, like for example, up here. And you can see if this graph is a CN, the cops can just close in on the robber. So from their initial positions, they can just both go in this direction towards the robber if the robber started on that side. And if the robber started on the other side, if the robber started over here, then both the cops will move in this direction to close in on the robber. And note that regardless of where the robber starts, the number of turns that it will take for the cops to close in on them will be less than or equal to n/4, approximately. So we can see from that we get an upper bound. And we can also see a simple lower bound. So wherever the cops place themselves in the cycle, we can see which way around the cycle is the shorter distance between the cops. So the way I've drawn it here, this is the shorter way. So if you want to take the shortest path between those cops in the cycle, you go around that way. And if the cops place themselves so that this is the shorter way around, then the robber is going to place themselves on the other side. at an equal distance between the cops, approximately. And if this is the shorter distance and the total length of the cycle is n, if that's a Cn, then it means that this longer distance here had to be at least n over 2. So half of that had to be approximately n over 4, at least. So that's why we can say the capture time of Cn is at least approximately n over 4. And again, I'll mention that Cn here, the capture time, we got approximately n over 4. With Pn, we got approximately n over 2. Based on these capture times, if we ignored the number of cops, it might look like from these two facts that it's harder to capture the robber on the path than it is on the cycle, which is not really true. It's just that the definition of capture time is using different number of cops for the cycle and for the path. So for the cycle, we're using 2 cops. For the path, we're using 1 cop. So this is really what's causing the difference, the n over 2 versus the n over 4. And here is a problem for you to think about. So let's say you have some spider graph S of order jk plus 1, and it has j legs of length k each. So remember a spider graph. This is a generalization of a star. So the spider graph, it has a center vertex. That vertex is allowed to have degree greater than 2. And it's the only vertex in the graph that can have degree greater than 2. So a spider, remember, it's just a special kind of tree. And it's a tree where only one vertex in the tree has order greater than 2. So this spider that I've drawn here, this one has k equals 3, and it has j equals, looks like 10. So that's a spider of order 31. And this problem is just to find the capture time of this spider. And remember, the capture time depends on the cop number. So for the spider, you'll also need to find the cop number, but that shouldn't be too difficult. So I wanted to discuss some well-known results about the cop number. Some of these are pretty simple, and some of them are very difficult, so we won't prove the difficult ones, but we'll talk about the simple proofs. So this first bound is one of the simple ones, and it uses the domination number. And we talked about this in class at some point. Domination number of the graph G. And domination number was just the minimum size of a dominating set for G. And dominating set, so we say S is a dominating set of G if every vertex in the vertex set of G minus S is adjacent to some vertex in S. So a dominating set of a graph is just a set that's adjacent to all the vertices in the graph. Or instead of being adjacent, it is equal to the vertex. So every vertex in the graph has to either be in the set or be adjacent to the set. And I claim that we can immediately see that the cop number of G is at most the domination number of G. And that's because if you do have a dominating set in your graph, so let's say we have some graph, I'll draw it. So our graph will start with some stars. So it has a few stars in it right there. And I'm going to circle a dominating set. Here's a dominating set for this graph right here. We can see that these three vertices, they're adjacent to all the other vertices in the graph. So that's a dominating set. Now, if I want to play the cop versus robber game on this graph, I can take that dominating set and I can just place a cop at each of those vertices. So a C there, a C there, and a C there. And we can see that regardless of where the robber places, anywhere in the graph, on the first turn of the game, one of the cops is guaranteed to be able to just move straight to that robber's vertex and capture them right on the first turn. So where I place that robber, any of the cops could have captured them. There's other places I could have placed the robber initially, and only one of the cops would be able to reach them on the first turn, like this cop right here. So we can see immediately the cop number of G is at most the domination number of G, and that's because given any dominating set, we can just place cops on each of the vertices in that dominating set, and that gives us an initial position for the cops at which they can capture the robber on the first turn of the game. Here's a very famous result about the cop versus robber game, and it's a really deep result. And the result, it shows that for any planar graph, the cop number has a small finite upper bound. And specifically, this result says that the cop number of any planar graph is at most 3. So given 3 cops on any planar graph, you can guarantee capture of the robber. And this result is very deep. It's a pretty complicated proof, so we're not going to prove this in this video, but it's a result that I wanted to mention to you because we've learned a bunch about planar graphs in this course, and this is a result about planar graphs. Here is an open problem related to this result, and this is not a problem for you to do like a homework problem, but an open problem that you might find interesting, which you could work on as a research problem. And the problem is to characterize planar graphs of cop number 1, 2, and 3. So it's known that all planar graphs have cop number at most 3, but it's not known which ones have cop number 1, which ones have cop number 2, and which ones have cop number 3. So that's a much more difficult problem than just proving the upper bound of 3. But it's an open problem, and it would be very interesting to know what the answer is. So here's another definition, and I wanted to find this so we can discuss a very famous open problem about the cop versus robber game. So this definition, C of n, it's a notation, and we use it to represent the maximum value of the cop number of G over all connected graphs of order n. I want to underline an important word here, connected. So if we were doing this maximum over just all graphs of order n, we could take, for example, some pretty pointless graphs. So we could take the empty graph of order n, which has n vertices and no edges. So a bunch of singletons like I drew up there. That graph, the empty graph of order n, I'll denote it as like 0 sub n. So this empty graph, its cop number is going to be n. It's disconnected. There's no edges in that graph. So if we had fewer than n cops, then there would have to be some vertex that is not covered by some cop initially. And that's the vertex where the robber would go for their initial position. And since there are no edges in this empty graph of order n, it means that none of the cops would ever be able to get to the robber's position. So the robber would evade capture forever if we had fewer than n cops. So you have to have n cops for the empty graph of order n. So for disconnected graphs, this Cn function would be not very interesting. So that's why we restrict it to connected graphs. And probably the most famous open problem about the cop versus robber game is Meniel's conjecture. This conjecture has been around, I think, since the 80s. And the conjecture is that the cop number of any graph of order n that's connected has an upper bound of big O of square root of n. And there are no counterexamples known to the conjecture. So the conjecture has been open for decades. No one's ever found any counterexamples. There's a lower bound that's known. So one of the best lower bounds that's known is this one by Prolot. And I say one of the best because I mean all of the best lower bounds that are known are of this form. C of n equals big omega of square root of n. And this is an example of one of these. So we can see that this is a big omega bound with the constant as the square root of 1/8. And there's other big omega of square root of n bounds. So there's many constructions that people have found to show that C of n is big omega of square root of n. And so Meniel's conjecture has a lot of evidence for why it makes sense that the cop number should be at least on the order of square root of n for some families of graphs. So many families of graphs, connected graphs, for which there's big omega of square root of n bounds. And there's no families of graphs that are known to have higher cop numbers. So this is why a lot of people believe Meniel's conjecture, because if it was false, then probably someone would have found some family of connected graphs of order n with higher cop numbers than these. So all the families that have been found of order n with high cop numbers, the highest cop number that's been found is just on the order of square root of n like this. Now, you might wonder, we talked about some lower bounds here, this Prolot bound and many others that are known. What about upper bounds? So Meniel's conjecture, what's the best upper bound that's known for this Cn? And the best known upper bound is only slightly sublinear. So that one looks complicated. You could write it like this. So that's the best known upper bound for C of n. So you can see that the lower bound and the upper bound, this upper bound down here, this lower bound right up here, they're very far apart. So the gap between these bounds, the gap is n to the 1 minus the low of 1 over square root of n. So the gap is approximately square root of n between the upper and lower bounds for C of n. So Meniel's conjecture is wide open, and this best known upper bound This was proved around 2010. The proof of that bound is pretty complicated. Later on, I think a year or two later, some other research teams found some alternative proofs of that same bound. So these two are the ones who actually proved the bound. They got it first, the best known upper bound for C of n. But there were some later research teams that found some proofs that are a little simpler, at least in my opinion. So one of the proofs that I've seen of this result, it's only written as a few pages, although some parts of the proof you could say maybe they could use a little more explanation. Maybe it would end up making the proof a lot longer. But this version of the proof, this very first version, is probably the most complicated version, and the later versions are a little simpler. But this is the best known upper bound, and these two are the ones who proved it first. So the reason why I mentioned Meniel's conjecture is because there's some related problems which we'll look at in a few more slides, and they're related to another optimization problem which has been considered for the cop versus robber game. So this one is a natural optimization problem, trying to find the maximum value of the cop number over all connected graphs. And there's another optimization problem which involves both the cop number and the capture time. So we'll look at that. And in order to define this optimization problem, we have to define a little bit more terminology. So we had this term cop win. We saw a bunch of examples of cop win and non-cop win graphs. We also have the cop number, smallest number of cops required to capture the robber, assuming everyone plays optimally. We had the capture time. This was the smallest number of turns sufficient for a cop number of cops to capture the robber. And notice that with the capture time, we were using the cop number of cops, which is kind of weird because it seems arbitrary in a way, because we were using a different number of cops on the path than we were using on the cycle. So with the path, we only had a single cop. With the cycle, we were allowed to use two cops. And so on the cycle, we got a lower capture time than on the path, even though the path, it only takes one cop to capture the robber, and on the cycle, it requires two, as long as the order of the cycle is at least 4. So another version of capture time that in a way is more natural to define is capped K of G. Capped K of G is the smallest number of turns sufficient for K cops to catch the robber. So you might be wondering, what if we have something like capped 1 of Cn for n at least 4? And capped 1 of Cn for n at least 4, that's going to be infinity. So if K is less than the cop number, then capped K will be infinity. Because if you use fewer than cop number of cops on G, then the robber can just evade capture forever. So the robber would never get captured. So we just write capped K of G equals infinity in that case. Infinity representing the fact that the robber just moves forever without getting captured. One more term. So this is the actual throttling, the title of the slide. And the throttling number of the graph G. So this is the throttling number down here. And this is an optimization problem. And we're trying to minimize over integers K. And what we're minimizing is K plus the capture K time of G. So this capped K of G. So we're trying to minimize the quantity of K plus capped K of G. So we're minimizing the sum of the number of cops and the number of turns to capture the robber. So we're trying to capture the robber quickly using few cops. And we can look at some simple families of graphs to see how the throttling works. So let's consider, for example, a cycle. So with the cycle, and we'll make it a pretty large cycle. So a cycle of order 50 here. So if we were just going to use the cop number of cops on the cycle, we would only use 2 cops. We would place them diametrically opposite. And the capture time, in this case, for a CN, it would be approximately n over 4 with 2 cops. So number of cops and the capture time. And with 2 cops, so with 2 cops, we said the capture time was approximately n over 4. And we can see that if we use 4 cops, then the capture time will be approximately n over 8. Let's see why that is. Well, we have 4 here, and we place them not just diametrically opposite, but we place them approximately at 90 degrees from each other. So if we think the origin here, we're placing them where each of the axes intersects the circle. So wherever the robber goes, like here, for example, these 2 cops just close in on the robber. And we can see that it takes approximately n over 8 turns at most for them to reach the robber. And it will take approximately n over 8 if the robber places themselves initially exactly halfway between 2 of the cops here. So 4 cops, the capture time is around n over 8. And if we did 8 cops, then the capture time would be approximately n over 16. And this generalizes. So we saw 4 was approximately n over 8. 2 was approximately n over 4. And if you use k cops, so if you use k cops, the capture time is going to be approximately n over 2k. So for the cycle, you're trying to optimize something that's approximately k plus n over 2k. And if you do try to optimize that and see what's the best value of k that you can choose, you find that the Throttling number of Cn is equal to the ceiling function of square root of 2n, that quantity all under the square root, and then minus 1/2. So it is approximately square root of 2n. And you can see here that if you choose the k, take k to be approximately the square root of n over 2. So what happens then? Then you get k plus n over 2k, and that would be approximately square root of n over 2 plus n divided by 2 times the square root of n over 2. And this equals, we'll write it as square root of 2n over 2 plus, we'll write this as n divided by, and this will be square root of 2n. and that's going to be square root of 2n over 2 plus square root of 2n over 2. And that gives you square root of 2n. So k plus 2k is approximately square root of 2n. And so that's how you can get that bound. And that really only shows the upper bound. So for the lower bound, you need to think about what we did when we showed the capture time of the path is approximately n over 2, and when we showed the capture time of the cycle is approximately n over 4. So what we did there, similar thing works here to argue that the lower bound is approximately square root of 2n.